All right, everybody. Thanks for coming out today. We are very lucky to have Professor Ted Rappaport, who is the David Lee Ernst Weber Chaired Professor of Electrical and Computer Engineering at the NYU Tandon School of Engineering, and he also has a laundry list of appointments in other departments at NYU. Most importantly today, he is the Neil Armstrong Distinguished Visiting Professor of Engineering at Purdue. He also received his BS, MS, and PhD at Purdue. So at NYU, he founded the NYU Wireless Initiative, or group center, the big entity at NYU in 2012. Before that, he founded WNCG at the University of Texas at Austin in 2002. And during that time, he was on my PhD committee, I might add. In 1990, he went to Virginia Tech, and he founded the MPRG group there. So he is a wireless pioneer. He's an IEEE fellow, a member of the National Academy of Engineering, and I could go on and on about Ted and list all of his awards, but we certainly don't have enough time for that. But thanks for coming out, Ted.
Thank you, David. Thank you. David, thank you for that kind introduction. It's terrific to be back at my alma mater. The campus looks great. This is a fun time of the year, no classes. You get a week to study for finals. I'm excited to talk to you about something that will impact all of us in this room. And for the students, this will impact your children and your grandchildren. And it's a message that I've been working on for a few years. I'm very passionate about it, and I think my hope is I think all of you will be passionate about this subject at the end of this lecture. So I'm going to talk about energy sustainability, and I'm going to narrow it down to the information, communication, and technology, ICT, telecommunications field. But this is a big issue, energy and power, and it's fascinating to look at the history of energy consumption on planet Earth. If you look at the history of mankind, it really wasn't until the Industrial Revolution in the 1820s that electricity and power became a thing on planet Earth. Faraday was inventing the idea of magnetism and generating energy from a moving magnet through a coil. The steam engine was being developed. It was really the 1830s where the energy consumption started to move from biomass, wood, foliage, leaves, into something that actually used energy to power machines. The Industrial Revolution is when you can see on planet Earth the primary energy consumption started to move upward. On planet Earth, up until about the 1830s, the whole globe consumed about 5,000 terawatt hours of energy. You're going to see that's a lot of energy, but that's everyone on Earth back then. But as the Industrial Revolution started to take hold and the locomotive was invented, you can see in the 1850s, 1860s, energy use started to climb. And oil was discovered in Pennsylvania, of all places, in 1860. And coal started to become an actual staple for energy because the railroad was developing. And you can see the energy usage broken down by fuel sources on the right. So we went from biomass to coal, and at the 1900s, the electrification started to happen when Westinghouse and Edison in the 1870s and 1880s started to create the electric utility. You can see around 1900, we started to double the energy ever used on planet Earth. You can see we went from 5,000 terawatt hours to 10,000 terawatt hours around 1900. And then the discovery of oil in Texas and natural gas pipelines started to fuel really the Industrial Revolution that took hold around planet Earth. But if you look at the energy consumption in the last 40 years, it's pretty dramatic, the amount of energy being consumed by our planet. If you look at from 1983 to 2023, just a year and a half ago, we've jumped to now 648, let's call it 650 exajoules of energy in a year. That's a big number. Say it with me, 650 exajoules. Ready? 650 exajoules. Come on, you can do better. 650 exajoules of energy consumed in a year. It's doubled. And if you look at the graphic here, you can see that it's starting to become hyper-exponential. And what I'm going to share with you today is really this is a concern because this is the tip of the iceberg. In fact, you look at oil and coal and natural gas, they're the primary energy sources. You can see the emergence of solar, wind, hydropower make up very small parts of that graph. But we are on a pace of energy consumption that's never been seen before. And it's likely just the start. Now, how big is an exajoule? We talked about 650 exajoules per year. It's 1 to the 10 to the 18th. So it's 10 to the 18th, and we're at 650. Very soon, we're going to be, up to 1,000 exajoules. And that's a lot of energy needs. And an exajoule is 277 terawatt hours. We all know in electrical engineering that energy is measured in joules, which is equal to watts times second, or kilowatts times hours, or terawatts times hours. But this is how big that is times 650 today around the world each year. And when you look at the reason for this rapid growth and you study the population growths in different parts of planet Earth, you can see that the population growth over the last 40 years has been remarkably steady in Europe, slightly decreasing in Russia and Japan. You can see Russia's in light blue, USA is in darker blue, a little bit of an increase, 2 to 3% a year. Europe's flat. Look at Africa. Africa has grown from 500 million to 1.5 billion people in 40 years. It's the most rapidly growing population on Earth, Africa. It's probably the biggest market opportunity, and countries around the world see that as a huge market opportunity. Look at China. China has gone from about 1 billion to 1.5 billion, and India with huge doubling of population from 750 million to 1.5 billion. So you can see Europe, America, Japan, relatively flat population growth. China and India and Africa with incredible growths of people. Now, not surprisingly, the energy consumption in these countries has mirrored the population growth. You'd expect that. But while Europe and Japan and the US, which are developed nations with developed economies, huge trade, they've been in a mode of curtailing energy use through regulation, through efficiency. And the developing countries, Africa, China, India, they've been opening up their borders and their trade really for the first time in the last 40 years with huge economic growth and population growth. What that leads to is the consumption of carbon dioxide emissions by country or by continent has really been remarkably different. You can see in red on the far left, China has ramped its energy consumption from about 40 exajoules in the year 2000, now to be the world's largest consumer of energy, about 170 exajoules. And you can see over the 40-year period, while the population growths have been roughly stable or increasing moderately, you can see green is Europe, blue is US, that the actual energy consumption has been flat or even decreased in Europe. Look at Europe. Europe's energy consumption is actually almost as low as it was 40 years ago, despite a nominal increased population. US the same way. And you can see also how Asia Pacific is growing in energy consumption, and you can see India, the violet down at the bottom, starting to ramp at 2023. The energy consumption maps directly to carbon dioxide emissions. And carbon dioxide emissions by themselves are not bad. Carbon dioxide is healthy. It keeps the troposphere protected. It protects us from UV rays. It provides protection on Earth. The trouble is when you have too much carbon dioxide, you start to have this global effect of creating a larger blanket where gases are harder to get out of the troposphere, and so you can have temperature rise. Now, I want to show you on the right the cost, or if you will, the carbon dioxide budget for a kilowatt hour produced by the various fuels that our electric utilities use. Oil, coal, natural gas, these fuel sources are naturally high when combusted in carbon dioxide emissions. Carbon dioxide, again, is not a bad thing by itself, but if we have too much, it has effects. Look at that. It's about 1 kilogram of carbon dioxide produced per kilowatt hour. That's a lot. A kilogram for coal, a kilogram of carbon dioxide when it's burned to produce 1 kilowatt hour. To give you an idea of a kilowatt hour, that's having a 1 kilowatt microwave oven on for 1 hour. So if you run your microwave oven for 1 hour, defrosting a turkey perhaps, you're spending a kilogram, 2.2 pounds of carbon dioxide. Oil is not quite as bad, but 840 grams per kilowatt hour. Natural gas is about half as plentiful in carbon dioxide than oil. And then you can see the renewables, which have received a lot of attention all over the world, and this is why. Look at the renewables, and this includes the cost of manufacturing the renewable energy, namely solar, hydropower, wind, and nuclear. Nuclear is getting a lot of attention. You're going to see why in a minute. But these are much, much smaller producers of carbon dioxide per kilowatt hour produced. This is politically charged. You hear the term global warming, which is a political hotbed. I'm not going to use that term. I'm going to talk about climate change. People don't like to say global warming because that implies a human activity has created the global warming, and no one was alive more than 100 years ago, so we don't know what happened 500 years ago. But it is true, we do know from carbon dating that the amount of carbon dioxide on planet Earth from carbon dating of ice crystals found in the poles has never been this high. So there is too much of a good thing in carbon dioxide. And what that has had by data-driven, is it's risen the temperature about 2 degrees Fahrenheit over the last century. In fact, you can see in 1911 is when the carbon dioxide amount in the world started to hit its previously known peak. And today we're about double that level. And the ramp is rapid. So I have a house on the Blue Ridge Mountains in Virginia. It overlooks Virginia Tech, where I started my career after I left Purdue in 1988. And this is the electric bill I got last month. And in it is APCO, Appalachian Power, telling me the amount of fuel they use to burn in producing the electricity. And you can see, since it's Appalachia, and you can see on the map, it's coal country, West Virginia, and where the railroad is plentiful and coal cars go by every day, there's a lot of coal, and you can see about 2/3, 66% of the energy budget or the fuel source for APCO as a public utility is coal. And they've got a little bit of wind and hydro and gas and solar. And what this really taught me is, you've heard the term politics is local. Energy is local. You see, APCO is local in the coal region of the US. And it kind of made me realize that the whole evolution of our fuel consumption in the world is based on where there's inexpensive resources to power our homes and to power the electricity. And when you look at the global consumption of energy and look at the fuel sources used by continent, something sticks out, which goes to this energy is local. If you look at renewable and clean energy, you see China is in red. They've had this huge population growth, and they are big users of renewable and clean energy, almost 35 exajoules in renewables. But their coal use is huge. It's over 90 exajoules. Roughly 1/7 of the world's consumption of power is coal from China, because coal is plentiful in China and it's easy to get to with railroads. So and look at the US. Look at the US in oil. We're the biggest consumer of oil in the US. we're at 35 exajoules in oil on the very bottom. And that's because oil is plentiful, especially in the Southwest. And natural gas, because the US and Russia went to natural gas when it was discovered. We have pipelines all over the country. You can see natural gas is huge with US and Russia, relatively huge for Russia, the light blue. Because natural gas is here, we invested, we have the easy transport. But when you take a look at this on a per capita basis, per person, you can see that the developed nations, namely America in dark blue and Europe, per person are the huge consumers of energy. US population, each person in the US consumes more energy than any other person in any other part of the world. In fact, a single person on average consumes 53 gigajoules of energy. You and I, in our daily life, aggregated with all the things we buy and the cars we use and the homes we heat, the music we listen to, and the AI chat GPT queries we do, we're burning 53 gigajoules per person. And that's in clean energy. And in China, coal is at 64 gigajoules per person. And oil consumption, we consume 104 gigajoules per person. So you can see we consume hundreds of gigajoules per person in the US. And when you look at it across the world, you could see indeed the per capita consumption on the bottom line. We consume in the US about 1 in 4 of every watt of power in the world per capita. So, and the gross, the US is at about 70%, China's at 31%, Europe's at 14%. So the reason why I present this data is to show you that the energy usage around the world is quite disparate, and it's historical from where the investments were made. And you can see that the trend, when there's policy to try to, awareness to try to reduce energy consumption, it makes a difference. Even with population growth, Europe has reduced its energy consumption, and per capita as well. So just to put these numbers back into perspective, if you had a 100-watt light bulb burning in your dorm room or your house, and you never turned it off 24/7 for a year, that single light bulb is burning 3 gigajoules of energy. You're consuming 3 gigajoules of energy just having your light on, little 100-watt bulb, 24/7 for a year. And I told my class yesterday, this alone should motivate you to at least be sensitive to turning the lights off when you don't need them. This is a lot of power when you consider that each joule we consume requires some energy source. Now, this is a big problem internationally, as you can imagine. You can see the haves, US and Europe, versus the have-nots, India and China emerging as great countries. You know, US and Europe are huge energy consumers. We have the lion's share per capita. And this has become a big issue. Maybe some of you remember at the end of last year, this conference of the parties, they've been meeting for 29 years. And they get together, leaders from all the countries of the world, to talk about the climate change issue, the haves versus have-nots in energy and the effect it has on the economies. And there was a bitter fight where some of the smaller countries in the Asia-Pacific islands, which consume very little power and are kind of at the mercy of all the big continents, they wanted some money. They wanted restitution to be able to invest in clean energy and do their part, and also to be paid for the price it's having on the climate. It affects, you know, it's getting hotter, and it affects their weather uncertainty. So these are the issues. They meet, and there's a big fight about it. And when you look at the energy consumption in the world, you notice that column goes down to a total of 445 exajoules. That's not the 650 exajoules we all said. That 445 is actually end-user energy. The other 200 exajoules are to make plastics, to make the materials, to go into manufacturing, to create the end products. So roughly 200 of the 650 exajoules goes into creating the world around us and not us consuming it as end users. So of the 445 exajoules, look at the ICT industry. This is the computer, communications, telecommunications, networking fields. It's close to my heart and to several of my friends who are in the audience. And if you look at that, the ICT industry right now is about 4% of the consumption of global energy. And it's interesting to compare it to roads and vehicles, which are about 20%, and residential homes, 20%. So 20% of the world's energy is consumed in the homes, 20% is consumed on roads and vehicles, and 11% is consumed in the chemical industry. Did you know that the creation of polyester and nylon is a big part of that 11% of the global energy consumption? So when you take a look at this, as an engineer working in the ICT field, I realize I better do what I can to minimize that 4.1% and try to lower it because it affects all of us. Well, how do you do that? So if you look at the typical communications industry, the user devices are cell phones, computers, laptops, tablets. They make up about 45% of the consumed energy in the ICT field. The network centers, the servers, the network operations center, 30%, and then the data centers. The data centers are right now 24%. Consider this. Google, Microsoft, and Amazon, leaders in the AI field, invested $200 billion 2 years ago. That's now up to $300 billion on AI, data centers, their business. That's almost 1% of the GDP of America. And it was higher than the entire investment of the US oil industry, which right now is the biggest producer of energy. So you can see the ICT leaders are investing more in their technology than the companies that fuel most of America. This is staggering. In fact, data centers are starting to go hyper-exponential. I don't need to tell you that. In fact, you could just see what's happened in our life in the last 2 years. If you look at the history of high tech, when I wrote my textbook in 1995 on wireless communications, which helped pay for a lot of kids to go to college and much more, at that point, the cell phone was the most rapidly adopted consumer device on planet Earth. Cell phone was in its growth stage in the 1990s. Well, that all got knocked out by Netflix, which hit 1 million customers in 3.5 years. Instagram hit 1 million users in 2.5 months. But when ChatGPT was announced, it reached 1 million users in 5 days. This was a slide presented by one of the executives at BlackRock, which is now using AI, and they're the biggest money manager in the world. And it had just come out. 5 days to reach 1 million users. It's unlike anything we've ever seen in adoption of technology. And these are old data now. This is old data from 2023. Goldman Sachs was predicting AI energy consumption would be double. It's going to be double next year, not 2029. And if you look back a year ago, ChatGPT, every time you did a query, it was 2.9 watt hours per single query. How many of you have done any ChatGPT queries in this room? We all have. When you look for something on Google now, it's doing a Google query. Google's at 0.3 watt hours. But still, it's 10 terawatt hours if scaled to 9 billion daily, and this is an old slide. This is 1.5 years old, so I'm sure it's far beyond that. In fact, AI is so power hungry that you see the big over-the-top providers reaching out to acquire nuclear reactors. You probably heard about 3 Mile Island. Microsoft is looking to acquire that or lease it long-term for energy production. The Vogtle nuclear plant, which was kind of in ruins, is now very interesting to Meta and to Alphabet. And NVIDIA 2023, these numbers are now eclipsed by about a factor of 10. That was 7.3 terawatts annually just in NVIDIA AI servers. And so this number's probably at 70 terawatt hours. That's a lot of energy consumed. And it goes on and on. In fact, now you can hear around the country and in Europe, the big over-the-top providers are seeking locations for their data centers very close to the pipelines for natural gas in the US, very close to hydroelectric dams. This is a big part of the growth phase of AI and the future data center. It's like the cellular telephone industry, which I know about, when it went from large cells to lots of smaller cells. And now when you drive the interstate, you can see a tower almost every exit. It wasn't that way 30 years ago. So they're looking to get power sources everywhere they can to feed this giant consumption of power. So I hope I've made the case that we're on an energy consumption tsunami. And when I started looking at this, I was fascinated to find that there's no common metric that this community uses to understand energy efficiency. We all know what a joule is, we all know what a watt is, we all know what a second is. But there is no standard industry acceptable practice to measure energy consumption by our industry. Shocking. In fact, many great people have said if you can't measure it, you can't improve it. If you can't monitor it, you can't optimize it. Yet that's where we are in the ICT industry, which is starting to go from 4% to 10 or 20% energy consumption on planet Earth in the next 10 or 15 years. So I took a look at all the different ways to consider energy efficiency metrics in wireless networks, data centers, circuits, AI/ML. They all have different standards, but none of them unify. There's not a fundamental metric. In fact, if you look at the wireless network field, my industry, ETSI, which is a European telecom standard body, and ITU, which is the International Telecom Union, and 3GPP, which is the global cell phone industry, all of them have different standards for energy efficiency. What's interesting, all these energy efficiency metrics are all based on different viewpoints. Look at the top one, it's for the network, where the switch is. Look at the middle one, it's for the base station site. Look at the base station site is the third row. And then for the RF, the radio frequency components on the cell phone and the base station tower is the fourth. And then 3GPP has some abstract idea. The point is, none of these unify. None of them have a fundamental common base. And then when you look at the data center, which you saw is 24% of the ICT industry growing hyper-exponential, there's this metric used by the big over-the-tops called power usage effectiveness. Power usage effectiveness takes a look at two different data centers, considers the energy being used for IT delivery and the auxiliary energy, the cooling, the heat sinks, the air conditioning, all divided by the IT energy. And this metric would show different data centers having different power consumption or energy consumption levels would have the same metric. It's well known that this is an abstraction. The whole data industry, the people that are looking for nuclear power plants are using a metric which is basically abstracting IT energy and auxiliary energy. Those are the only components they look at. This, I thought, was very unusual because so much is at stake. Why would you abstract it that much? And then look at in circuit design. Do we have any circuit designers in here? RF circuit design? Good for you. I love it. There are two different definitions for power added efficiency for a radio frequency amplifier that's in all of our cell phones. And the first definition has the power consumed in DC supply plus the input power and the output power, two different definitions. And then for the linear noise, low noise amplifier, which is also an amplifier, you have a totally different metric. The point is there's no fundamental metric for circuit design. And IEEE is starting yet another study group to try to measure energy efficiency. So this, to me, as a researcher, was staggering. What is a professor to do when you see a problem and you don't see an answer that has a fundamental basis? Well, this really perplexed me. And I don't know what you guys do for fun, but every 7 or 8 years, what I like to do for fun, this will tell you a little bit about me, is I like to go to the beach and I take this old, rat-eared paper copy of Claude Shannon's information theory paper, and I read it on the beach. And the second paper I read on the beach is Harold Free's noise figure paper. I love Shannon and Fries. They were Bell Labs pioneers in the 1940s. As you know, Claude Shannon, working with Warren Weaver, invented information theory in the 1940s. And Warren Weaver and Claude Shannon came along before there was anything called digital modulation, before there was anything called binary digits. In fact, Claude Shannon invented the term binary digit. But Weaver and Shannon would study the Morse code telegraph channel in their research papers, because Morse code, even though it was still in use in the 1940s, it was the only real digital communications known to mankind. And they studied the Morse code, which eventually allowed Shannon to write his famous information theory paper. And Harold Fries, he created Fries free space path loss. You know, you blow a piece of bubble gum and the bubble gets big and you suck the bubble gum back in and you got all the bubble gum. You didn't lose any. No energy was created nor destroyed. That's how Harold Fries described how you radiate a signal from a transmitter. It goes out like a big sphere and the antenna intercepts just a small part of that sphere. So these papers I love to read for fun because they're so amazing. And what I love about them is they got down to the basic fundamental definition of something which stuck for the rest of the world. In fact, when you look at Shannon's entropy paper, a mathematical theory of communication, he was studying how atoms and molecules worked by a guy named Boltzmann 50 years ago who was trying to figure out how gases turn to solid. And he was trying to find the fundamental metric to call for information because Boltzmann was in search of the fundamental thing. They didn't know the atom existed yet. They hadn't found the electron when Boltzmann was doing it. But he was searching for the fundamental basic form that you could build something on. In fact, if you look at his theory of this paper from 1948, you can see he's defining his famous entropy. And he said the entropy will be a probability of system being in cell of its phase space. He's referring to Boltzmann's phase space of matter, trying to get to the very essence, the very fundamental root. I call it the unit vector. He was looking for the unit vector of information. In fact, Harold Fries was doing the same thing. Harold Fries was trying to understand noise in a radio receiver, try to get a fundamental metric that everyone could measure the performance of a receiver. Because back in the 1940s, 1944, noise was the enemy of communications. And there was no way to quantify it, compare how good this receiver was to that receiver. And you can see, again, he goes back to the fundamentals of the noise in a resistor, a Johnson noise, and comes up with his famous 4kTB to define noise figure. And today, every receiver made on planet Earth measures its ability to receive based on this fundamental metric of noise figure. And you can see noise figure, very elegant, but very simple. Very simple. It's simply the signal-noise ratio into the signal for signal out of the signal. And his famous parameter, F, noise figure, now is on every receiver you buy. You'll find it if you look in the fine print. So, you know, I had this brilliant student at UT Austin around 2008, 2009, James Murdoch. And James was a genius. I couldn't convince him to stay for a PhD. But he was fascinated with a perpetual motion machine. He was fascinated with energy consumption. And he comes into my wireless group, and he was my star student in the EE440 equivalent. And so I recruited him. And EE440 is the senior communications class if you're not in EE. By the way, I was a TA for that here back in the 1980s. And a lot of fun. So, and it's a great class to get into grad school if you're looking to go into communications here. I think Professor Love teaches that, don't you, David? Yeah? So he was in that class and he said, I want to do a perpetual motion machine. I said, well, you know, people have studied it throughout history. We've never found it. And he said, well, I'm going to try it. And so he got into Turing machines and computing, and he came back very frustrated every few weeks. He'd like, I tried this, and I can't do it, and there's this loss, and there's this loss. I said, well, why don't you look at communications? Because we don't really know how to measure energy. Why don't you look at energy consumption and see if you can find a way to define the losses in a communication channel? And he comes back very excited after I told him to read Harold Freese's paper. I said, James, what I do every 7 years is I go to a beach. Take these papers and read them. So he went off and read the same papers that I did, and he came back a few weeks later with this idea of consumption factor, a figure of merit to measure energy efficiency from any source to any sink in a communication channel. And we honed the theory a little bit and found out, wow, we're really onto something. We've got something that gets down to the essence, just like Shannon did the unit vector of information, and Freese did the unit vector of noise. I thought we had found the unit vector for energy consumption that could unify the entire industry. In fact, the idea is very simple, which is what you see in Shannon and Freese work. The ideas are pretty simple once you've cast them. But until you see them, the world's too busy doing their own thing to kind of get around a metric. And what we realized is if you look at any source of information to any sink of information, wireless, optical, computer, data, doesn't matter, any source to any sink, that there's always going to be a signal path which the information travels on. And there's always going to be off-signal devices. Think of in your cell phone, the signal devices are going to be the amplifier in your phone, the antenna, the radio channel, the receiver, and the off-signal paths are your keypad, your display, your power supply. So we broke every possible source to sink into these components, off-path and on-path. And we focused on the on-path. And what you can see is on the on-path, we were able to go back to Shannon's fundamental definition of bit, binary digit. In fact, that's what made information theory, Shannon's ability to quantify the unit vector, the simple basic measure of a bit. And we went back to Shannon's theory and found that we could use Shannon's theory in this approach to energy consumption. In fact, we published the paper. The math was very messy, but some of my students went on to industry. Nokia used it for a HAPS, high altitude mobile cell phone. And then I had another group of students, and I said, this math is so hard to use. Go back and look at Freese's paper and see if you can cast the math exactly the way Harold Freese did. And because I had a hunch you could. And sure enough, you could. So we published this in 2024 and then published these two papers and found out that the mathematics are as elegant and as simple as Harold Freese to look at the energy consumed over a communications path. In fact, here's the idea. It's very easy. W, which is now our waste figure, is simply the power consumed divided by signal out. That's really just 1 over efficiency in most systems. Efficiency is how much you get out versus how much you consumed, right? How much got out versus total consumption. That's efficiency, less than 1. If you inverse that, it's greater than 1. So the waste factor is basically 1 over efficiency. And when you look at the source and sink power, it turns out that this metric, very simple, 1 over efficiency, can be used to provide a cascaded formula to understand energy consumption for any communication channel. In fact, when you cast the waste figure for each cascaded component, just like Harold Freese did for cascaded components in a receiver, as long as the system is linear, which is a fair assumption in communications and computers, if you have a linear cascade from any source to any sink, you can identify the efficiency of each component and look at the gain of each component ahead of it and come up with a total waste factor of the signal. And the beauty of having this metric, W, waste factor, is that the total consumed power is simply the output power times W. If W is 1, all your consumed power is in the output. If W is greater than 1, you're not getting all the output. So if you treat that on the bottom equation, P signal out, you just measure your output signal and multiply it by the waste factor of the cascade. That tells you how much power you consumed. And then you just add the non-path power to it. Whatever the ancillary power consumption is, you add to it. So this is the world's first approach to quantifying in any communication system a very elegant formula for understanding energy efficiency from any source to any sink. In fact, 1944, Harold Freese published his famous noise factor. In 2024, we've published waste factor. Notice the similarity? In fact, the only real difference is that Harold Freese was looking at a receiver with the source at the antenna being noise. And so he refers noise figure to the input of the receiver. We look at waste factor and refer it to the output of a device, because you can measure the output power. It's measurable. By the way, just like Harold Freese, you could do referring to the input or the output. We could do the input or the output. But we choose to refer to the output because you can measure it. You can see it. You can put it into an A to D and then do AI and optimize it. So we measure output power, and compared to the consumed overall power of that device, we have W. So this is a very elegant formula, and I just learned that the ITU is considering it as a fundamental energy metric, which I'm pretty excited about at an upcoming meeting. Now look at this. Look how elegant this is. I just want to show you how fundamental this is. So those of you in communications are very familiar with the top formula. It's noise factor. Waste factor is new. But all you need to know is the gains of the system cascade from source to sink, and the waste factor, the efficiency of each module. That's all you need. So look, it works for a resistive attenuator. You have a source, you have a sink, you have a loss, just like in noise factor, where the attenuator loss is equal to the noise factor. The waste factor is equal to the attenuator loss, because the wasted power is the loss, and that's what W is, wasted power. And if you have a transmitter with a source to sink on the upper left, this is called a homodyne transmitter because that is a single modulator. This is what a small IoT device would look like, when you open your car with your remote fob, or turn your fan on in your room with your remote. This is similar structure. You can see you can now use the waste factor efficiencies. This is from mini circuit spec. This is right off the spec sheets of different components. You can now see which design is going to use less energy by using the waste factor. Very simple computation. Didn't exist before. And furthermore, what's amazing about waste factor that Harold Freese never could do, because Harold Freese was looking at noise just coming into a receiver, waste factor doesn't care if it's a transmitter or a receiver or a channel. Because a channel is like an attenuator, right? Put your signal in, signal out, it's an attenuator. So amazingly, you can get a waste factor of the channel. This opens up whole new areas of research for multi-user communication, signal design, analysis of power efficiency for cellular architecture. All kinds of new areas opened up, and we've just started to publish on that. But the idea is that the loss of the channel is 1 over the gain, which is the waste factor of the channel. And once you have the waste factor of the channel, and you know the components of the transmitter and the receiver, you can build the cascaded system with the same formula and find out that in typical systems, this simplifies. If you have a receiver gain that's much less than the path loss of a channel, typically a satellite receiver or a cell phone receiver. Typically the receiver gain on Earth, we're gonna have 120 dB in our cell phone, 120 dB dynamic range. Satellite link might be 200 dB, right? 200, that's 10 to the 8th more. So this is very typical. So the system waste factor, how much power you're consuming, how much energy you're consuming, a metric that we could all keep score with, is simply defined by the loss of the channel plus the waste factor of the transmitter, minus the gain of the receiver. This is a very elegant result, which now allows us to determine energy efficiency and compare different architects. It also works in circuit design. Remember that PAE? Well, it turns out that W equates to both of those equations. So you can cast all of the circuit design power amplifier metrics in terms of the waste factor. And the waste factor is simply 1 over the original PAE that's not used that much. And the current PAE, which is widely adopted, power added efficiency, relates to simply the gains and the input in the DC power. Now, data centers, this was the most remarkable result, and this won the Best Paper Award at GlobeCom in 2023 when we presented it. The entire industry for data centers is using PUE. Remember this power usage effectiveness? Different data center sizes can have identical PUEs, but is it the best figure of merit? It's not. We took a look at data centers, and when we looked at the data center, we saw that they were abstracting the power used in IT delivery. If you get down to more of a basic level of what's in the data center, you have power used in the information transmission, and you have power that's not in the information transmission. Remember, waste factors from source to sink, right? So it's got to be an information flow. When you look at the components in the data center that are carrying the information, not storing, but carrying, you find out that the abstraction used by the data center industry is hiding where the work is being done. I mean, what do you use a data center? To communicate data, right? Communicate. They're missing it in the figure of merit. And when you look at the waste factor for data centers and you break it into the information and non-information powers in what they're calling the IT power, you find out a remarkable result. That is, you find out that what the world right now thinks is equally good data centers, they're actually missing the point that this data center A, which consumes more energy, is actually much more energy efficient. It's got a waste factor of 1.286, about 15% less than 1.5. So it's 15% more energy efficient in communicating the data, the job a data center is supposed to do. But the industry doesn't know this yet. I'm trying to get them to wake up to this. This is a very important result because data centers growing so fast in energy consumption. Finally, look at waste factor in a cellular architecture. This is a problem we have with 5G today. Carriers don't know this. Wireless carriers have been slow to invest in 5G infrastructure, even though the equipment is much more energy efficient. It's been designed to be more energy efficient, but they don't know it. If you look at A and B with the same energy efficiency by the ITU metric, they think they're the same energy. In fact, here's the energy efficiency from the ITU metric. 24%, the power in the signal versus the total power consumed. But if you use waste factor, you find out that the waste factor of the 5G system, which has less power in the non-signal and more, it's got more power in the non-path, but much less power in the non-signal, it's actually more efficient. It has a waste factor of 3 compared to 3.5. In fact, a lot of carriers think 5G is more expensive to operate. But that's because the ITU metric has the nominal lightly loaded area built into its metric. It's abstracted power consumption for when it's lightly loaded and not lightly loaded. The quiescent power is stuck in there. And what they don't realize is if they pull out the quiescent power and the non-quiescent power for when it's loaded, which is important in a cellular network, waste factor brings out the real power consumption of all the transmission, and you could save power by going to the 5G base station. And they don't know it because all their software and all their monitoring is based on the ITU metric, which hides all that. In fact, when you look, this is the waste factor, this is the energy efficiency metric defined by ITU. You can see how their metric, used around the world, is a function of the transmitted signal power. In any linear system, you don't want a metric that's a function of power. But yet their whole energy efficiency theory is based on a metric which is a function of the transmitter power. Transmitter power function is not information flow. When you look at the energy efficiency metric with waste factor, you see that it doesn't matter what the signal level is because waste factor has brought out the components of communication versus quiescent. So the industry's missing that. We're trying to get the word out. And the beauty is now we have a metric, just like in Harold Free's noise figure, just like in information theory, where we had a fundamental metric, a bit, to be able to quantify information and to decide which codes are good, which codes are bad. Noise figure tells you which receivers are good, which receivers are bad. Now we have a metric, a very simple metric, waste factor, which can tell you when you're designing well, when you have a low waste factor. Remember, a W of 1 is perfect, right? And an open circuit is a W of infinity. A W of 1 means all the power out is the power being consumed. So you want W as low as possible. So if you have a low W and high data rate, that's optimal. If you have a low W but a low data rate, you can use the fact that you have a low waste factor to increase the transmitter power and increase the bandwidth with no cost on energy. And if you have a high data rate but a high waste factor, you can now replace the base stations with more power efficient or energy efficient infrastructure, which is what needs to happen in the move to 5G. And then finally, if you have a high waste factor and a low data rate, you're being very inefficient. You need to replace the base station with a lower waste factor product and a smaller cell size to get lower energy consumption. And Nokia is starting to look at this. Huawei's been using this. So the industry is slowly catching on, but I think the biggest gains to be had are in the data center field, where that entire industry is spending so much power and is missing the boat on understanding the energy used to communicate bits versus everything else. And we've published this in a paper, if you'd like to see it. It published last year. The engineers at Huawei in France really jumped onto this and are using it for their products. And we hope to have it in other telecom products. But I think the big gain of this will be in the data centers and in AI. So in conclusion, the world is facing an energy consumption tsunami. I hope you all saw that, and you might think twice about turning off the light or the stereo when you leave the apartment for an hour. I know I do. It's changed my perspective. And we've lacked a unified figure of merit for energy consumption and energy efficiency. Just like Harold Frees and Claude Shannon went to the basics of physics, they went to the natural laws, like Boltzmann, looking at Johnson noise and the molecules and trying to find the basic state, the unit vector. This, I think, is a way forward for a unit vector for understanding energy efficiency. It's based on the natural law. Basically, energy consumption is based on energy consumption and efficiency multiplied by the gain. So it's a unifying figure of merit. It works across all these domains. It's pretty simple. But it took 10 years and 3 generations of graduate students to get the math into a way that I could see how simple it was. So I think we need similar metrics for the off-path power or computation. I asked an NVIDIA VP, what's your figure of merit for energy consumption? He said, well, it's flops per bit or something, or flops per operation. I said, no, give me a metric like Joule. Give me a fundamental metric. And they didn't have one. So we need to get something like this for computing and the off-path power. With that, I want to thank you. Go Boilers, hail Purdue.
All right, thanks, Ted. I think we have time for questions. I'll try to bring the mic to you.
Okay, so correct me if I'm wrong. So all the smartest engineers in the world that work at all these companies that basically generate all of this economic activity for the United States, like the whole stock market, missed the ball because they didn't know where to draw the lines in their systems and which fractions to add up? Is that what it was?
You know, it's that no one has been able to take the time to study the fundamentals of energy consumption. So all the industry is busy with frenetic economic activity, creating committee-based standards. And the people come in with their own bias and they make standards by committee. That's how your cell phone and Wi-Fi works. It's all standard by committee. This is the beauty of fundamental research and the beauty of the academic enterprise, where you can, and that was the beauty of Bell Labs. Don't miss this. That was the beauty of Bell Labs, where they had the freedom and the ability to think about things that had no economic value at the time. Certainly, this had no real use case when James Murdoch came into the office excited with all that math for consumption factor. But I'll say the bottom line is no one has put forth a figure of merit like this, which unifies across many different source to sink combinations.
Other questions? I'll ask one for you, Ted.
Sure,
so
Dave.
if I apply this to backscatter, is it getting the power for free, or would I somehow lump that in as a...
I'm actually working with students at Texas A&M on reflective intelligent surfaces, which are a lot like backscatter. And it turns out you can use this theory to answer that. And there's a waste factor for your backscatter element. It will be the amount of power consumed and how it powers itself to how much is transmitted. And you could put that into a channel loss equation and answer that. So the beauty of backscatter, I don't know if you're passive or active, but you could harvest power to make it active, or it could just be totally reflective. And that's really just creating multipath. It just changes the gain of the channel. So what you're doing is, going back to Harold Freese, the Harold Freese free space path loss, you chew a piece of bubble gum and you blow this bubble. That's the or you drop a pebble into a pond and those waves come out spherical. A receiver captures a certain area of that bubble. You know, the farther away I am, you get a little bit less of the bubble, right? That's why receive power gets weak with distance. So all backscatter does is it gives you a little more area, surface area of receiving. So it's like you're blowing the bubble and you're receiving part of the bubble and you get a little bit more.
All right,
Does that make sense?
Yeah, definitely. Thanks.
Can this metric consider the effects of the bandwidth used for any digital communication system? Because we're thinking about, I'm a circuit designer, so I don't think as much on how does the modulation scheme is affecting my circuit. I just make sure that I have enough bandwidth. But can this metric ensure that if we're comparing OFDM, for example, to the older, 3GPP, for example, is it better to have a more advanced digital communication system?
Yeah, no, what this can do, this absolutely can do that, as long as it's linear. If you're operating OFDM in the linear range and back off and your signals are linear, you can then compare energy efficiency for anything going in and out. So just like Harold Freese required the bandwidth in his noise figure to be at a certain limit for all the stages, I haven't thought about bandwidth per se, but you're going to apply the same limit that Harold Freese did. As long as you have an operating bandwidth that's defined for the gain and efficiency of each cascaded device, it will work. And the reason why it will work is you're just looking at an input signal, the signal power versus the total power consumed of your circuit. That's all you need to know. Or the output power. The output power of different modulations will define the efficiency of those, of your circuit. You follow me? I actually talked about this in the James Murdoch paper of 2014, where you use Shannon's limit and the bandwidth and the data rate to kind of wrap it in. But I'll be honest, I've not published on that, and I don't think anyone has. So I would encourage you to look at using waste figure for your circuit design. Just look at it, see what your circuit is on the probe station, see what your output power is for input signal, look at your total consumed power, define W, and then try different modulations and see if it changes, see if your circuit changes, see what changes. But I bet this works. Professor Leonard, yes. I had his coding class when I was a student.
Okay, Ted, I just wanted to know if you wanted to say anything when the communication engineers try to maximize their noise figure. They scrutinize the first stage to get the first stage preamp with the best possible noise figure. Do you want to talk about the parallel setup?
I didn't mention that, but it's exactly the same. Professor Leonard properly states that you always want to minimize noise figure of your first stage, the preamp. Just like you want to minimize the preamp noise figure in a receiver, you want to maximize the power efficiency of the last stage of your transmitter or your last stage of your circuit. In fact, you can see the theory of noise figure exactly matches that. Here it was. Just like, so you can see in this equation on the top, F1, if F1 is the smallest possible thing on the top equation, the lowest possible noise figure, ideally 1, and if you have a big gain in that device, you can see the big gain carries through and makes all the other components de minimis. Exactly the same way, Jim, you see W sub n in my bottom equation, that's the nth or the last stage. If you make Wn the most energy efficient, drive that closer to 1 with high gain, you can see all the rest of the terms have a high gain in the denominator and don't matter. So the first terms in Harold Freeze and the first term in waste factor both drive the overall metrics if the first stage, or in my case, the last stage, is a high gain. Thank you.
Any other questions?
Hi, Professor. Thanks for the wonderful talk. I just wanted to ask, where do you see the future of wireless communication going, provided like I have worked in a wireless product-based company, and not a lot of people are interested in millimeter wave or like paying more for the subscription services, since we have already achieved a good downlink and uplink speed on the cellular communication. So where do you see the future of wireless heading towards?
What did you say, PWA? What were you saying you're working in that people aren't interested in? I missed it.
Millimeter wave.
Oh, millimeter wave. Oh, that's a topic I like to talk about. So millimeter wave, believe it or not, millimeter wave is doing much better than most academics really believe or know. The fact is, millimeter wave is creating the largest profits and opportunities for the carriers in the US through fixed wireless access and through supporting high speed in venues. Every stadium, every downtown district is using millimeter wave. Academics don't know that, and that's because they're not in the real world, but I talk to the real world, and millimeter wave is growing very rapidly. Now, T-Mobile was very late to adopt. They just bought US Cellular, but T-Mobile is the one that really didn't like millimeter wave and made very loud noise about it because they didn't own any millimeter wave spectrum, and they were doing really well with their 2.5 gigahertz midband spectrum. So there was a lot of confusion thrown in there, but millimeter wave is growing rapidly, and it's used quite a bit. So the future of wireless, though, is the midband spectrum, upper midband, in the 6 to 24 gigahertz range. Governments around the world have all agreed that that's going to be the big 6G. They're going to call it FR3, Frequency Region 3. FR1 was the first 4 generations of cellular. Each G or generation takes 10 years. Everything was below 6 gigahertz. Millimeter wave was the first move above 6 gigahertz for 5G being deployed around the world. And 6G is going to have FR3, the third frequency region between 6 and 24 gigahertz, between microwave and millimeter wave. And so that's the big excitement. That's where all the research is. That's where a lot of the funding's going. And you're going to see spectrum auctions in 3 or 4 years for those bands. But the future of wireless is very bright. I'm just hoping we can make it a power-efficient future.
Any other questions?
Since you mentioned that waste factor, we can deduce the waste factor for the channel itself.
Yes.
So does it mean that we can deduce other metrics that are relevant for communications, like
exactly
SNR,
right.
SINR, channel capacity, and those kind of things?
Precisely right. You got it exactly. Just like noise figure lets you trade off different components which are noisy or not, waste figure allows you to trade off cellular architectures or wireless architecture. So if you have a channel with less loss, you could trade that off with perhaps a less efficient receiver, which is in fact what we do. By the way, did you know that the cellular industry right now, the most efficient base stations have a waste factor of about 3. The mobile devices have a waste factor of about 20. So our mobile devices are very inefficient because the carriers know that you have to pay your own electric bill. But you start adding up billions and billions and billions of cell phones, we could do something better than that. We could drive the waist figure down in each mobile device. We could all do our share. But you're exactly right.
Any other questions? All right, so thanks, Ted, for that very inspiring talk. It's great to have you out to Purdue.
Thank you very much. Thanks for coming out.